Remember, this graph that I've drawn is for zero external field. Okay, this graph. This is, you will only get this graph for a ferromagnet for zero external field. Now we would like to describe this behavior with the help of the Weiss's molecular field theory. Okay. So what happens in an antiferromagnet? Once again, there is a molecular field that is set up. Now we can subdivide this structure into two sublattices magnetically. Two magnetic sublattices. One is plus and the other is minus. For the plus sublattice, we know that the magnetization is going to be given by ms bj as a function of y. Now what is y here? Y is gj mu b j over kbt into a field. Now what is that field? There could be an external field B and there could be an internal field. Now that internal, where is that internal field coming from? For a ferromagnet, the internal field was lambda m. Here. This is what we had for an internal field. This is our y. The internal field BMF was proportional to the magnetization of the sample and given by this Weiss molecular field constant. Higher the magnetization, higher was the internal field. Okay. Now what we have here is that the magnetization of this one domain, one sublattice, is being governed by the molecular field that it sees, which in turn depends upon the magnetization of the other sublattice. So when the magnetization of the other sublattice goes up, this magnetization should also go up. You see, if you move on this graph like this, this negative magnetization, negative in the sense negative spin or spin pointing down, the oppositely magnetized domain, if the magnetization goes up in the negative sense, this magnetization should go up in the positive sense. So once again you can introduce a molecular field which now depends upon m minus the magnetization of the other domain. Okay? Some constant lambda, the minus sign, because if this thing is negative, then if this thing is negative, it goes more negative, this goes more positive. That's why you have this negative sign over here. For a ferromagnet, there is no distinction between the two subdomains. There is just one domain which is magnetized, and the magnetization for a ferromagnet. Now I'm going to write the ferromagnet. For the ferromagnet M, there is just one M equals ms bj as a function of y. Now y is gj mu b j over kbt into the external field plus lambda m. So this is the molecular field term, lambda m. Higher the magnetization of the ferromagnet, higher will be the field that the domain sees. Okay? So this is like the chicken egg problem I mentioned earlier on. Because higher the magnetization, higher the molecular field, but the higher magnetization is coming from the molecular field itself. So it's like a chicken egg kind of scenario. What comes first? But this is the model. The model for a ferromagnet says that the effective field a spin sees depends upon the externally imposed field and the molecular field that has been generated by the magnetization of the sample itself. That's why it's called an internal field as well. In this particular case, there are two subdomains labeled by plus and minus. The magnetization of the plus domain, or one domain, depends upon the molecular field generated by the other domain. That molecular field will be larger in magnitude when the magnetization on the other domain is large. So it's proportional to m minus. And this is just a constant again. This minus sign makes sure that the two magnetizations are in opposite directions. M minus is negative, this thing is positive. If this goes more negative, this becomes more positive and the magnetization of the plus domain goes up. not attraction, but there is an interaction, an antiferromagnetic interaction. So the antiferromagnetic interaction is tuned into the system through this term. Remember, it's a model, and it's a very valid model. Okay. So look at this thing over here.
But this sublattice plus its own
Magnetization, that's going to affect the magnetization of the other subdomain. So if you look at the other subdomain, the magnetization of the other subdomain, M minus, that's going to be given by Ms, Bj, and the Y relevant for the other subdomain, which is Gj, mu B, J over KBT. The same external magnetic field is seen by both the domains within the same structure minus lambda. I would like to make this lambda absolute, M plus. So it's a totally symmetric interaction between the two subdomains. The magnetization of the beta domain or the second domain is dependent on the magnetization of the first domain. The molecular field that this domain sees depends upon what the magnetization of the other domain is. That's how you enforce or incorporate antiferromagnetic interaction between the two subdomains into the model. Okay. Now if you look at this expression and you look at this expression for a ferromagnet. For a ferromagnet, if we put B equals 0, we were able to define the Curie temperature, the transition temperature for the ferromagnet. That Curie temperature, Tc, is, I should remember this but I don't, this is equal to Ms J plus 1 Gj mu B lambda over 3kB. Okay, this was the Curie temperature. This was the temperature for a ferromagnet at which the slope of the Brillouin function at y equals 0 matched the slope of the curve that related y with j at 0 field. Right? This is how we define the Curie point. Now, if you look at this expression, and this expression, okay, and you look at this expression, do you find any similarities? They're almost identical. How do I know that they are identical? If M plus, and this is how an ideal antiferromagnet is defined, if M plus equals minus M minus, which is how an ideal antiferromagnet is defined. Remember, this is negative, this is positive. Okay, so minus of this gives me a positive M plus, and if I call each one of these M, then I look at the relationship, the molecular field relationship for an antiferromagnet. M, I can write M equals, if I look at the top one, Ms Bj, Y is Gj mu B over KBT J, and if my field is 0, I have minus lambda M minus, which is just lambda M. Okay, minus M minus becomes M plus. Okay, so there's M plus here, but each M plus equals M. So for each subdomain is behaving just like a ferromagnet. Each subdomain, whether it's the alpha or the beta subdomain, each one of them is behaving like a perfect ferromagnet. Okay? If you look at these curves over here, this curve is for a perfect ferromagnet. This curve is for a perfect ferromagnet. So for each one of these subdomains, we can define a similar critical temperature. And both of the critical temperature for each subdomain is the same, because each one of them has the same value of Gj, J. Both domains are identical in that respect. This is not the case for a ferrimagnet. For an antiferromagnet, an ideal one, both of these quantities, these constants are the same. So we can define a corresponding critical temperature for an antiferromagnet, which is called Tn, the Neel temperature. This Tn is defined in an analogous fashion. It's Ms, the saturation magnetization of each subdomain, which could be 1/2 the number of spins per unit volume, because half of them may be in the other domain. Not necessarily half, because you have other kinds of like spinel structures in which 1/3 are in one kind of structure, 2/3 are in the other. But nevertheless, this is a saturation magnetization for each subdomain into J plus 1 Gj mu b lambda over 3kb. So we can define a critical temperature or a Neel temperature for an antiferromagnet as well. So this defines the temperature at which an antiferromagnet undergoes a phase transition and becomes a paramagnet. So now what we would like to do, we would like to find out the susceptibility of an antiferromagnet beyond its Neel point. Okay, beyond its Neel temperature. Remember, if you are below the Neel temperature of an antiferromagnet, the magnetization is 0. So it's really hard to study antiferromagnetism because it does not leave its footprint. Its magnetization is 0. It does not produce a magnetic field. It does not produce a demagnetizing field. It does not have any shape in isotropy. Okay? So it's very hard to study antiferromagnets for this reason. Below their critical, in their magnetized state. Remember, it's a highly ordered magnetic state, but unmagnetized. That's why they're so hard to study. However, if you would like to raise the temperature of an antiferromagnet so that it goes into the paramagnetic state, makes a phase transition, then you would like to draw a susceptibility versus temperature graph similar to a ferromagnet, similar to a paramagnet, and you can tell the difference from that. So what you would now like to do is you would like to find out the susceptibility of an antiferromagnet beyond its Neel point. In order to calculate susceptibility, once again you turn on the magnetic field. Y is small, so you use this 0th order expansion, the first order term inside the Brownian function. You get m plus equals ms djy. The first order term is j plus 1 over 3j into y, which is gj mu b over kbt. J external field b minus lambda m minus, right? Okay. M minus is likewise ms j plus 1 over 3j gj mu b kbt j b minus lambda n plus. Okay, the expression that I wrote over there. Now the overall magnetization of the sample beyond the Neel point is just going to be the sum of these magnetizations, remember? So what we have is m plus pointing in one direction, m minus pointing in this direction. It's just a vector sum, or it's just a sum of these. If I'm taking one of them to be negative by my definition here, then the overall magnetization is m plus n minus, right? This is negative. So this is the overall magnetization of the sample. Now I'm going to add these terms. Remember, this is Weiss's molecular field theory. Now I add these terms. M equals m plus m minus. When I add these terms, I get ms j plus 1 over 3 Gj mu b kdt to be minus lambda m. Now I will use my expression for the Neel temperature. M is J plus 1 this thing is this thing over here, and it's a constant, a characteristic of that particular antiferromagnet. Okay? So what I could do, I could rewrite this in the following form. My M equals Pn over lambda to b over T minus Tn M over T. So this becomes M1 plus Tn over T equals Tn over lambda T 2 times P is my mu naught, H is M over chi. Okay, this means my chi is my susceptibility for an antiferromagnet beyond the Neel point is 2 times Tn over lambda T mu naught 1 plus Tn over T. This is 2 mu naught Tn over lambda T plus Tn. This once again is a constant. Remember, for an ideal antiferromagnet, we have these terms. Both of these lattices are the same in all respects. They only differ in the orientations of the magnetization. This is an ideal antiferromagnet. A ferrimagnetic material is one in which the two lattices are different. They have different magnetization. So there isn't a complete cancellation of the magnetizations. That's a ferrimagnetic material. Now, if you look at this expression over here, chi is turning out to be proportional to 1 over T plus Tn for an antiferromagnet. For a ferromagnet, this was turning out to be 1 over T minus Tc, the Curie point. For a paramagnet, this was turning out to be proportional to 1 over T. Now we can plot all of these together. Chi T paramagnet. Suppose this is my Tc for a ferromagnet. This is my curve for the ferromagnet. Now suppose I have, this is my Tn. How do you make the plot for an antiferromagnet? This is how I do it. Right? And this is going to approach this. But so it starts off from here, but this is meaningless here. It's only defined for T greater than Tn. So this is its asymptotic, this dash curve shows its asymptotic approach of this curve, which is only valid for temperatures beyond Tn. So this is how the three kinds of materials differ. Alright? Now what we would like to see, the general form for the Curie-Weiss law is that the susceptibility is 1 minus T minus some constant theta. This is called the Weiss temperature. For an ideal ferromagnet, this is the Curie temperature. For an ideal antiferromagnet, this is negative of the Neel temperature. Okay? And remember that this temperature, which is theta, can be different from Tn in magnitude even. The critical temperature might be different from the Neel temperature, because we have taken into account a simplistic model over here. If we include a more complicated model, for example, and this is question number 2 of your homework, if my M equals Ms Vj, now my Y equals external field plus some dependence on, this is M plus, some dependence on the other magnetization, plus some dependence on M plus itself, then you can get a critical temperature which is different from the Neel temperature. The Neel temperature is always defined like this. So you can get two different temperatures, the critical temperature as well as the Neel temperature. The susceptibility is defined for temperature beyond the Neel temperature, but the asymptotic approach is to a different critical temperature. You will get behavior of this kind. And in fact, for antiferromagnets, the critical temperature could be wildly different from the Neel temperature. And I have a table that I'll show at the end that exemplifies this. Now the question is, I would like to see, is what is the susceptibility of an antiferromagnet below the Neel temperature? We know that the magnetization might be 0, but what about the susceptibility? The susceptibility, we all know, is dm by d. This is the susceptibility, right? In the limit that b is 0, right? Applying a magnetic field to an antiferromagnet might cause a change in the magnetization. Okay, because this graph is for 0 magnetic field. What if we do apply a magnetic field to a ferromagnet? That's the question. So what we would like to see is, we would like to see how does this graph looks like in the presence, and what does the susceptibility look like when the temperature is below the Neel temperature, when you are in this regime. Remember, another way of plotting these graphs is by plotting 1 over chi versus T. For an antiferromagnet, if this is my Neel point, if this is Tn, the graph would look like this. Okay? Minus Tn. So what we would like to see, what is the susceptibility at temperatures below the Neel point? This is what we would like to explore now. We'll do a semi-quantitative argument here. So what happens here in this region? This is what we would like to see. Now that it's an interesting problem. Now you have two magnetized domains, M plus, M minus. And both of these are saturated. Please, I draw a circle here. Suppose I'm at 0 kelvins. When I'm at 0 Kelvin, each one of these domains is at its saturation level. So the radius of this circle is ms. And I'm at T equals 0. Now what if I apply a magnetic field? I would like to see the response of the system. Now, interestingly, it depends upon what is the direction of the applied field. There are two possibilities. One possibility is that the external field B is applied parallel to the axis of the antiferromagnet, the magnetization axis of the antiferromagnet. That's one possibility. Now if you look at this possibility, will the magnetization change as a result? Now this field is aiding this magnetization, but its magnetization cannot go beyond saturation level because all the spins are perfectly aligned anyway. This magnetic field is arresting, or this is not aiding this magnetization, but it is at the saturation level. At 0 Kelvin, this has to remain at the saturation level, so its magnetization cannot change. Okay? So what's going to happen is that the magnetization is not going to change if we apply a small magnetic field in this direction. Small magnetic, remember there are small magnetic fields. So the susceptibility of this configuration is at 0 Kelvin is 0 if we apply the magnetic field parallel to the magnetization axis. Now suppose the temperature is slightly above 0. We're in this regime somewhere. So in this regime somewhere, the magnetizations, of course, they are not at the saturation level. This is M plus, this is M minus. Now applying an external field parallel to the magnetization axis will have a profound effect. What the effect will be is that this magnetization will grow, can grow, because there is room for it to grow. It can move towards the saturation level. And this magnetization can now decrease. When this magnetization grows, this magnetization decreases, the magnetization of the overall sample goes up, which means that the susceptibility is now non-zero. You keep on increasing the temperature, the susceptibility continuously goes up, 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 and up. The magnetization goes up, the susceptibility goes up. So this can also be done in a more quantitative way, but that's beyond, I don't have time for that. So the susceptibility takes a linear response between 0 and Tn. At 0 Kelvin, the susceptibility is 0, because at 0 Kelvin you apply a small magnetic field, nothing changes. This magnetization cannot go up, this magnetization cannot go down. Okay. How can a magnetization go down? It can go down by twisting, but the field is not strong enough to twist this. It's already at 0 Kelvin, so it has to be saturated. Okay? Or another way to look at this, if this is a perfect antiferromagnet and this is saturated at its maximum value, then this must be saturated at its maximum negative value because of the antiferromagnetic coupling. Okay? So now this graph of the susceptibility is observed when the applied field is parallel to the magnetization axis. So this is the susceptibility in the parallel configuration, when the field is parallel. What if the magnetic field is applied perpendicular to the magnetization axis? That's the second kind of scenario that can arise.
So before that, the first case at 0 Kelvin for a ferromagnet, wouldn't we have the same effect as this temperature?
Yes, it is 0. So if you, but it also depends upon Yes, it's going to be 0. Magnetization, susceptibility or magnetization? The magnetization is really large. It is at its saturation value for a ferromagnet. नहीं होगा तो the susceptibility at 0 Kelvin is going to be 0. Okay, now what we would like to see is what happens if we have the same scenario at 0 Kelvin, M plus, M minus, and we apply a small magnetic field in this direction, perpendicular to the quantization, to the magnetization axis. Alright, now if you look at this kind of argument here, what happens when a magnetic field is applied to a magnetic moment? It applies a torque. Now the direction of this torque on this field, on this magnet is like this, the direction on this magnet is like this. So these magnetizations tend to slightly change their angles. They still remain at their magnetization saturation level on the surface of the circuit. This kind of an antiferromagnet is called a canted antiferromagnet, in which the spins are not totally antiparallel, they make a certain angle. This is called canted antiferromagnetism. Now if you have this configuration, we would like to find out, suppose this angle is phi. We would like to find out the susceptibility. Now let's find out the susceptibility. Let's find out first the energies of the system. Now we know that the energy of this system is going to be given by this magnetization. There's a molecular field on this magnetization due to this magnetization. So the energy due to this interaction is given by minus this magnetization M plus into the molecular field imposed by this. Now the molecular field imposed by this is lambda M minus. Correct? So this defines the interaction between these magnetization, these magnetic moments. Now each one of these is also has a Zeeman energy inside this external field. This term describes the interaction between these movements. Now, due to the energy due to this moment placed inside the field is given by minus M plus E. Minus mu dot B, right? Due to this, it's minus M minus 1. Now this is minus lambda let's call the magnitude M, so M square. What's the angle? This angle is 180 minus 25. So it's cosine of pi minus 25 minus 2 times M B cosine of 90 minus 5, which is sine phi. Now what is cosine of pi minus 2 phi? This is sine of 2 phi minus sine of 2 phi. So you get plus M square sine of 2 phi minus 2 MB sine of phi. Oh sorry, cosine of 2 phi. Sorry, cosine of 2 phi. one thing I missed, the molecular field is minus this, so I get a plus here. It's actually minus n plus BMF, right? And BMF is minus lambda minus, right? Okay. Sorry. Now this is my energy. Now if my phi is, I can also write this in the following form. Energy equals minus lambda n square. What is cosine 2 phi? It is 1 minus sine square of 2 phi. 1 minus sine square of phi. I say cosine of 2 phi 1 minus 2 sine square of phi minus 2 mb sine of phi. Now if phi is really small, because this field is really small, hence this is minus lambda n square 1 minus 2 phi square minus 2 mb phi. This is the energy. Now when will the energy be minimized? If this system is to remain in a state of equilibrium, we can find out the angle which minimizes the energy. That angle is given by the derivative of the energy with respect to phi. So if I take the derivative of the energy with respect to phi, I can calculate the minimum energy. This is 4 lambda m square phi, 4 lambda m square phi minus 2 mb. This is 0, which means that my phi equals b over 2 lambda m. This is the angle which minimizes the energy. So if I apply a small magnetic field, the equilibrium state of the system is when the angles are this much. Okay? Now what is the energy? For the energy, I put this back into the expression for the energy. So my energy is, the minimum energy in the equilibrium state is going to be equal to minus lambda m square 1 minus 2 phi squared, I think, square of this, which is b square over 4 lambda square m square minus 2 mb 2 lambda m. Now the magnetization of the sample must be given by the negative of the gradient of this energy's derivative with respect to the field. You are at 0 Kelvin, so this is just the free energy. So I have to differentiate this with respect to B. So I get this 2 lambda m square, I get another 2 B over 4 lambda m square n square minus 4 mb over 2 lambda m. Let me do some cancellations. So this gives me mb over lambda minus 2 oh, B over lambda minus 2 B over lambda is minus B over lambda. This is minus I forgot this negative sign is also here. So this is minus plus. This is plus B over lambda. This is mu naught Hm chi over lambda, which means my chi is mu naught over lambda, and this is the susceptibility when the applied field is perpendicular to the magnetization axis. It's independent of temperature. So the other branch of this susceptibility curve is this one, chi perpendicular. So once you get into the antiferromagnetic regime, the susceptibility depends upon what's the direction of the applied field. There's a parallel susceptibility and there's a perpendicular susceptibility. And you get this anisotropic effect. If you have a polycrystalline sample in which there are many crystallites and each domain is pointing as a different magnetization axis, then you will get a curve that lies somewhere in between. So the susceptibility is now directional dependent inside an antiferromagnet. Now a really interesting thing happens when this magnetic field is large. It's large. You see, there's an internal molecular field. That internal molecular field makes these domains go in opposite directions. But if the external field that you impose is so large that it swamps the internal field, it washes away the internal field, then the effect of the external field is going to dominate. Okay? So in the last 2 minutes, I'd just like to give an interesting example of what happens there. If you have a situation in which the two magnetic domains are pointing in opposite directions but they're collinear, but you apply a magnetic field, you're still at 0 Kelvin. Nothing is going to happen. You suppose you perform the experiment always at 0 Kelvin, you're not raising the temperature. What I would like to see is what happens with magnetic field to the magnetization. Of course, you're at 0 Kelvin, so the susceptibility is 0 for this configuration. So the magnetization doesn't build up because the susceptibility is 0. But then eventually you build such a large magnetic field that it forces this magnetic domain to flip. But it doesn't flip in such a way that it just becomes parallel to the field and it goes on top of this. It's going to flip in a canted fashion. What's going to happen is, at a certain critical field, these two domains will go and switch at a certain field in this fashion. So this becomes n plus, this becomes n minus. This angle is phi, this angle is phi. So they will become canted, suddenly at a certain magnetic field. And you can find out the field, the amount of field that produces this. This is called a spin flop. So a certain spin flop is produced, and overall the sample acquires a magnetization. You can find out the field that is required to produce the spin flop by energy consideration exactly in a similar fashion as I've done. How would you do that? Whether it is energetically favorable to have these domains pointing in opposite directions for this field, or is it energetically favorable for these domains to be pointing like this, to be canted like this at a certain angle phi, at a certain field. So you compare this energetically with this energetically, exactly in the same fashion as I've done over there. You look at the interaction between these domains and the interaction of each one of them with external fields and compare the two energies. And see, you will see that at a certain critical field, certain B, at a certain B, which would be given by this thing over here, at a certain B, it becomes more energetically favorable to have this configuration. And when this configuration, suddenly a magnetization appears, right? It's not at the saturation level, but still there. So at this point you get a sudden peak in the magnetization at this critical field, V1. Now what's going to happen if you increase the field even further? Then these magnetizations, a torque will act on them and they will be pulled in towards the external field. And the magnetization steadily grows in this fashion. Right? You see, the magnetization is steadily growing until you reach another critical field at which the two domains become parallel, and then you reach the saturation magnetization, and this is the graph that you get. So if you look at the spin configurations or the domain configurations, they are like this. Here they are like this, here they are canted, and here they are parallel. So this is a spin flop transition. You can also have another kind of, if this axis, if the magnetization likes to remain pinned to this axis. Why? Because of magnetocrystalline anisotropy. We'll learn more about it. There might be certain axes inside the crystal, and the magnetization likes to remain pinned to that axis because that is energetically favorable. Okay? If the magnetization likes to remain pinned to this axis, it does not like to go into this canted orientation because that costs energy. So for such kind of materials, it's possible that the transition from this state to this state, remember it's a ferromagnetic, from the antiferromagnetic to the ferromagnetic state does not occur through the intervening path of canted ferromagnets. It directly goes at some field V3 to the spin flip state. It directly goes there. This is called a spin flop or a metamagnetic transition. Oh, sorry, spin flip. This is spin flip. Spin flip. The spin immediately flips. And if you're at finite temperature, the only effect that happens is that these boundaries get smoother. Now, these kinds of metamagnetic transitions do occur in certain materials. Okay? So, in the last slide that I would like to show you, just two slides to show you an actual result from an article. So the first table I would like to show you is a list of common antiferromagnets: chromium, manganese, nickel oxide, iron oxide, manganese fluoride. Most fluorides and oxides of nickel, iron, cobalt are generally antiferromagnetic. Chromium is also antiferromagnetic, and this is the kind of structure they have. This is the Neel temperature. The third column represents the Neel temperature at which the phase transition occurs. The fourth column represents the critical temperature to which the graph asymptotes. And you will notice that the critical temperature could be totally different from the negative of the Neel temperature. There's almost always different, because the simplistic model that we assume must have additional terms in which you have to include intra-lattice couplings as well. Okay, so this is a graph, a table of the common antiferromagnets, and in this graph you can see how the magnetization of a lithium, it's a single crystal of a manganate, I'm not sure which, this is the reference, in which if the field is applied parallel to the c-axis, the top left curve A, if it's applied parallel to the magnetization axis, you can see these spin flop transitions at certain magnetic fields, and this is a zoomed in view. Okay, you'll see a curve at 5 Kelvin, a spin flop transition, here another spin flop transition, and these are extremely large magnetic fields, by the way. And if you applied a magnetic field perpendicular to the magnetization axis, which is graph B, you do not see any spin flop transition. The spin flop transition is only for strong magnetic fields that are parallel to the magnetization axis. In our next lecture, we'll discuss ferrimagnets. Look at some structures, important structures of ferrimagnets. We'll discuss helimagnetism. And if we have time, in the next lecture, we'll look at spin waves, the spin wave formalism and magnons. Inshallah, see you next time.